Okay, I think we need to get started. Welcome, everyone, to the first of our Mastering Casino Data series. This is the first of 4, possibly 5 sessions related to analytics and data, which we all can agree impacts all casino marketers, regardless of their positions or titles. The series is going to be divided into 2 sections. This first section addresses many of the hot topics we're all reading about, perhaps still struggling with, and AI and machine learning are always top of my mind when it comes to this. Before I let Andrew get started, just to tell you a little bit about this session, one of the things that we wanted to tackle were sort of the buzzwords and defining the terms that you're hearing, and understanding how techniques can be applied to casino marketing and perhaps where they shouldn't. My hope with this is to give you a strong foundation to have discussions with your internal teams as well as vendors, both existing and potential. This session, as well as all of them, are going to be recorded, and you're going to receive a link in a day or 2 so that you can rewatch it if you would like. And Q&A is available. There's a little button down below where you can submit your questions. I'm going to keep an eye on them, and as will Andrew. And so we may answer some of them midway through the presentation. Some may come at the end, but if you've got questions, please put them in the Q&A box. And finally, I also want to mention, in case you haven't heard, that we've been expanding Casino Marketing Bootcamp, not only with our master classes and great webinars such as this one, but we've also doing regional editions of our signature bootcamp events. So while our signature event takes place in New Orleans and continues to approach marketing sort of in a 360-degree view of what casino marketers do, regionals have been developed specifically for the markets and the topics that are currently and in the near future sort of on their plates. We're going to be in the beautiful state of Washington this October. And like our signature event, the group is intentionally limited to a small number. We've already gotten some registrations. So if you're interested in coming to Washington in October, take a look at the agenda online and let me know if you have any questions. And now I'm going to turn it over to Andrew.
Thank you, Julia. Thank you all for being here. Let me get started. Sorry, have to get Zoom all set up. So yeah, as Julia mentioned, we're going to be talking about artificial intelligence, data science, and machine learning today. And this is the first of, as she said, 5 sessions, 2 that I'm going to be working on, focused on these topic areas. And today, the real goal is to help you understand, what is this? What is all the buzz? Why are people talking about it? Why should I care? When people come and talk to me about it, what are they saying? What do those words mean? This is going to be a relatively general introduction to machine learning, AI, and so on. It's meant to give you the tools. In 2 weeks, when we come back together, we're going to talk about some of the difficulties and the things that you need to think about to be successful. Some of them are just business things you need to worry about, but some of them are casino specific. But we know AI is very buzzy right now. I work in the AI industry. We talk to customers across industries. It's very rare to go into a customer where at the board level, they're not having, what is our AI strategy conversations. So everyone's talking about it. And that tends to filter down. And it filters down, interestingly enough, into a number of places, one of which is marketing. That's, what are we going to do in marketing about this? That tends to cause a little bit of panic. So what are we talking about? Before we begin talking about it, why should you even listen to me? I am a data scientist. I'm a practicing data scientist. I've been doing this for 15 years. I'm very overeducated as well. I have my PhD in a somewhat unrelated area. I tend to be a little bit cranky because I've spent 15 years here. I've seen things come and go. So I have a little bit of a cynical attitude. You'll see that in our conversations today. But I think it benefits you to see that it's not all rosy, like people say. But But among other things, I've worked as a math professor, spent 15 years as a data scientist. I got my start building credit card fraud models. So if you've ever had a credit card declined and got a message from your bank saying, hey, we think fraud happened, I worked on one of basically two products that did that for the banks. I spent a fair amount of time in marketing analytics for casinos, but also for consumer electronics, worked in a wide variety of places, and spent 4 years up until 2020 working at a company called Data Robot, which is an AI vendor, platform vendor, leading their entertainment vertical. So I was working with customers across entertainment. And so that included movie studios, music studios, gaming companies, sports teams, and a number of casinos, both physical casinos, but also online casinos. So I've worked with these people to understand how to bring this in, how to make it useful. And then I have to mention this, as I always say at the beginning, this is the one slide my boss requires me to include. He's paying me to give this presentation, so he wants at least a little bit of a plug. So I'm currently the chief data scientist at a company called Rosgo. It's a little bit farther removed from this, but it's about all of those business metrics you're collecting. How do you make it easy to interact with them, evaluate them, do deep dives into them? The one thing that may be interesting to hear on here is if you're looking to get in contact with me, my LinkedIn and my Twitter are both relatively easy to remember, Angle Analytics. You are welcome to reach out to me if you have any questions. You're welcome to reach out to Julia and she can put you in contact with me as well if you don't remember this. I'm happy to answer questions if they come up after this. So let's start. Everyone's heard this phrase, right? This came out in the late 2000s. Everyone was saying data is the new oil. I was already working as a data scientist when this became popular. To be honest, I didn't like the phrase data scientist, and I really, really hate this phrase. This isn't right. This isn't really what you need to think about. Data sitting unused has no value. Casinos have a lot of great data, all of that Players Club data, all of that slot machine data. But if you're not using it, it's not providing you with any value. It's simply a cost. And so we have to get past the sense of just collecting data. We have to do something meaningful with it. It turns out that this phrase actually came from a quote by a man named Clive Humby in 2006, and it's a very small portion of that quote. And what he said was actually much more important. What he said is data is the new oil. It's valuable, but if unrefined, it cannot really be used. It has to be changed into gas, plastics, chemicals, et cetera, to create a valuable entity that drives profitable activity. So must data be broken down, analyzed for it to have value. I really like this quote. I don't like data is the new oil. People seem to stop at that point. But this piece, it has to be changed into gas, plastic, chemicals, et cetera, to create a valuable entity that drives profitable activity. This is data science. Whenever anyone talks about what is data science, this is what it is. It's taking the data you have and getting value from it. So let's start with the buzzwords. We've heard these. If someone comes to you and they're talking about artificial intelligence, I'd be worried. We've actually been hearing it just this week. Google fired the individual who came out and said that he thought one of their chatbots had achieved consciousness. Now, to be fair, he wasn't fired exactly for his beliefs. He was fired because he was releasing internal details about Google and violating NDAs. But still, as much as we'd like to believe that those chatbots are not sentient yet, they're very good, but they're not sentient. So anyone who begins talking too much about artificial intelligence, be worried. Be worried. It's much farther away than they're willing to let you know.
So Andrew,
yeah.
Let me ask you, do you feel like chatbots, which we all have experience with, are sort of the the entry point into artificial intelligence for consumers?
I think it's the one most consumers have the most interaction with. Although, well, it's not just chatbots, but Siri, right? If you're talking to your phone, Siri is very, very impressive. Alexa is impressive. Even Google Voice or the Google product is very impressive. Those are artificial intelligence. They're effective, they're useful, no denying it. They're not intelligent yet, right? You can see that. You can ask Siri something and you get some really strange answers at times. The next step down is deep learning. We'll talk about what deep learning is. We'll explain what it means and where it comes from. Most of these tools, most of these artificial intelligence tools that are being built are using deep learning as the technique. They're very powerful. These are the tools that give you image recognition, video processing. If you enjoy sports and you enjoy seeing them track the ball or something like that, that's what they're using. They're still not that valuable in most business settings. And we'll come and talk about exactly why that is. So there's some hype. If a company comes to you and they're going to sell you a deep learning solution and they're selling you, hey, I'm going to make your marketing 10 times more effective by identifying the right customers to market to, it's probably really high buzz. If they came in and they went to your security department and said, hey, we have a way of tracking individuals for you, maybe. The next step down is machine learning. We'll describe what that means. Anyone who comes and talks to you about machine learning at this point probably actually has something real, or they would be using one of the other buzzwords we've already talked about. Traditional predictive modeling, we'll talk about this. This is really just another way of saying machine learning. Again, if someone's willing to talk about terms that no one has thought was buzzworthy in 5 to 10 years, it may be that they actually have a real product. And then someplace in the middle is data science. And there's a lot of value in data science. There's a lot of people who've had success in data science. There's a lot of history of failures in data science. It's very buzzy. The industry loves to talk about it. We all talk about the shortage of data scientists, how hard it is to hire data scientists. But there is some real value and there's some amazing things coming out of the data science community. So it's someplace in the middle. And we'll begin to describe what each of these are as we go forward. Okay, so I gave you the quote and I said, that's really what data science. Let me actually make it a little bit clearer. Data science is the science and the art. Art is important here of using data to solve business problems, right? This is the goal. Data science is not meant to exist as, hey, I've got cool data, what can I do with it? Data science is really meant to exist of, I have a business problem. I have a churn problem. I have a customer acquisition problem. I don't know how to spend my marketing budget. These are business problems. What data science is supposed to do is say, okay, you have that business problem. Can I help you use the data we already have to make better decisions than you could make in the absence of that data? It's all we're trying to do. And I'm going to keep coming back to this, business problems. Whenever you think about data science, always think about the business problem first. If you're talking to a vendor, keep the business problem you're trying to solve in mind the entire time. And the reason is data scientists tend to think about the technology, the solution, what they're doing. That's the fun bit, this miracle. They don't really care about that end at the other end. And so they will tend to not ignore it exactly, but diminish its importance. You need to keep bringing back that business expertise. Okay, so let's go through and what does this stuff mean? Machine learning, it simply means learning from the past to predict the future. AI is any system able to perform tasks that ordinarily require human intelligence. So Julia, you mentioned the chat box. We talked about Siri, but it's actually any decision making. If I'm an automaker and I need to decide how many cars to produce next month, and I build a mathematical forecast for demand for next month, that's AI. It also tends to be machine learning, but AI is this broader set of all of the things. I'm old enough when I got started in this field. Actually, before I got started in this field, I had an introduction to so-called expert systems. Expert systems were really popular in the 80s. They were still somewhat popular in the 90s. Some of you may have seen these, but these are just rules. Basically a big tree of if this, then this, and just pull it out that way. And they tended to be hand-built by experts. These are really powerful. If you're a physician and you need to make a diagnosis, oftentimes you're running one of these sets of rules in your head. Is it this? Okay, I check that. Is it this? Okay, I check that. Airplanes run on this. You think about the checklist that the pilots go through in the cockpit. They're running through this manually, but we can have a computer do exactly the same thing. AI, therefore, is everything and nothing. And that's why it's so buzzy, is what does it mean, right? It means all of these things. Okay, so when we think about it, and then there is, in here, I grabbed this document or this image. This is the deep learning piece. Deep learning is a specific type of machine learning. And we'll talk about exactly why that is and how it differs or how it's a little bit more special. And the reason I say machine learning isn't very buzzworthy is because when you look at all of the value produced across all of the AI solutions, the vast majority of value is produced by these machine learning tools. So I said I got my start in credit card fraud modeling. This is a $100 million a year problem for most banks. They're using machine learning solutions to try to minimize that, save themselves $20 million. Those solutions drive a lot of value. Take a step back. Every time you do a credit risk, every time a bank makes a credit risk decision, so you apply for a loan and they decide if they're going to give you, they have machine learning models running to forecast effectively your likelihood to repay that they then use to make that credit risk decision. That's a multi-billion-dollar problem for most banks. So massive amounts of money. And then there's a bunch of, we'll call them the boring AI solutions. These are the expert systems that exist and run in the background. They work really well. Don't get me wrong. In fact, if you can solve a problem with an expert system, do. They tend to be much cheaper and easier to understand. And they can provide a lot of value. As of today, a very small portion, a tenth or a 20th of the total amount of value is being driven by deep learning. That'll change. It'll get bigger as we get better at it. But if you're not Google or Facebook, where it is a big deal to you, it's very unlikely to drive a lot of value. Okay, so my math reference, this is your machine learning system. Yes, you pour your data into this big pile of linear algebra. So for those of you who've taken linear algebra and maybe hated it back when you were in school, that's all we're doing. We're having the computer do a massive amount of linear algebra, and then the answer comes out on the other side. And then this is the other piece. This is kind of a black box even to the data scientists. And so the only way we know if it works is to look at the answers. And if we don't get the answers we expect, we tend to go back and just try making changes either to the data or to the algorithm. And we'll talk about wrong answers and what it means and how you evaluate it. But that's all this is. This isn't even really complicated math from a high-level mathematics perspective. Linear algebra is generally taught in the sophomore year to math majors. So it's a relatively early math class that we're leveraging. When we think about machine learning, there's two kinds of machine learning, supervised and unsupervised. It means exactly what you think it does. There's a target in supervised learning. So I know what's going to happen. So let's say I want to know if one of my patrons is going to churn. I know historically whether or not that patron churned. When we build a model, we take advantage of that fact to reward the model when it gets the prediction right and punish the model when it gets the prediction wrong. So supervised learning is based on, we already know the state for these, we can learn from them. Unsupervised learning is more of, I have something here, but I don't know what it is. The classic use of this is in things like computer security, where I have this massive amount of traffic and I've been hit by hackers and I just don't know it. And so what I'm looking for is anomalous things, things that are unexpected, things that don't look like everything else. You can think about this as insider fraud. So if you're looking at data on a casino floor and you're looking at, are there machines they're paying out at a rate that we don't expect, right? You can just put all of the payout data into an unsupervised learning algorithm and have it not tell you there's something wrong with that machine, but rather there's something different about that machine. It could be it's in a weird location and it gets used weirdly compared to all of the others, or it could be there's something physically wrong. Unsupervised learning can't tell you which it is. It simply says it's weird. Both are very useful. Supervised learning tends to be easier to get money out of because you're much closer to, I know what I'm going to do with the answer. Whereas unsupervised learning tends to be, oh, that's weird. Now I need to go do something to investigate it further. So it's a step removed. In supervised learning, we think about supervised learning again in two different ways. Classification models. So it's one of those, there's a class that this exists in. We want to predict that class. So it could be binary. Does the patron churn? Does the patron not churn? It could be multi-class. Maybe I'd like to forecast which of my marketing bins the patron's going to end up in a month from now or a year from now, so I can make future plans. Well, you have more than two classes. You have multiple bins that you're going to forecast them into. That's multi-class. But it works very similarly. They're all classification models. I'm going to keep coming back to this because when you talk to vendors and even when you talk to a lot of data scientists, they will gloss over or maybe not even acknowledge this. When you ask for a prediction of will this customer churn or will this customer not churn, most of these systems will say churn or not churn. But what's actually happening under the hood is that it's returning a probability of churn. So what it's actually going to say is this patron has a 60% chance of churning, or this patron has a 20% chance of churning. And from a marketing perspective or any business perspective, this is really, really powerful because the difference between someone who I classify as churn with a 51% chance and a 95% chance is immense. I absolutely want to take action against that 95%. The 51% may or may not. There's a second reason this is really useful. You have a limited resources to do something about this. Maybe I've got so much money in my budget to attack my churn problem. Or maybe I've got so many hours in the day that I have people who can reach out to these people if I'm thinking about my high net worth customers. That probability allows you to rank order them and say, this is my most risky, my next most risky, my next most risky. And now we can begin saying, okay, I have a list that I can prioritize. So data scientists tend to ignore the fact that there's a probability there. Business owners tend to ignore the fact there's a probability there. It's actually really, really useful to you to understand this. And to give going back to the credit risk example, this is why banks don't look at, are you a credit risk or not? They look at like your FICO score. Your FICO score is a mapping from the probability of default, more or less, not exactly. It's also inverted because the higher numbers are better. But this is what they're doing. This is why they're saying, oh, you're above 800, you're pristine credit, we don't have any problems with you. You're above 750, you're almost pristine. You're above 700, you're almost certainly going to get a loan. And then as you get into that 600, 650, this is where they begin making their decisions. And it's based on exactly that. How much risk do I want to take on? How much money do I have to loan? All of these questions. So just to give you an example, I do have a math background. I have to have a little bit of mathematics. I try to keep it visual. This is a graph. This is a 2D graph. I'm assuming there are two classes. We can probably guess the two classes are the blue circles and these red crosses. And when I build a classification model, what I'm effectively asking for is some sort of surface or line through this that separates the two classes. I think looking at this, you can probably, if I asked you to hand draw a line that separated these, you probably could. It's going to look something like that. And then what we would say is anything below that line, we can define that mathematically as in the red class. Anything above that line, we'd say mathematically is in the blue class. This is great when your data is pristine. Your data is never this pristine. You almost certainly have mislabeled data. You have unexpected things. If we talk about customers who churn, I can't get every single customer who churns because some people churn for reasons that are unrelated to anything I could ever see. I have a local casino. One of my best players gets a job offer on the other side of the country and moves. That customer is going to churn, right? There is nothing I can do about it. And it's potential that nothing in their play, because they may have to move at the drop of a hat, would ever give me any sense that something's changing. So we're always going to have those misclassifications. The other thing to think about when we talk about this is you're never going to build a solution that's perfect. You're always going to have errors. You have to be comfortable with that. So the other type of problems we think about is regression models. If you remember, perhaps not so fondly, linear regressions or building linear regressions in Excel, it comes from the same thing. The goal is not to predict a class, but to predict an outcome, predict a numeric value. These could be continuous or discrete, but they tend to be some sort of numbers. So how long is it going to take me to get someplace? How much is someone going to claim for? How much is what is someone's ADT going to be next month, if you will? Or what is this particular patron's future value to me as a casino? So those would be regression models. And again, it's exactly the same thing, but this time we don't say, is it above this line or below this line? We say, oh, I have this value 4. Oh, the prediction is slightly less than 0. That's all we're doing in regression models. Deep learning are machine learning models. They can be used for classification or regression. The difference is they use what's called a neural net to do it. And a neural net is based on a neuron. You can think of broadly that your brain is a neural net. Don't take this metaphor very far. Some data scientists do. It isn't quite like a brain. It is inspired by biological brains. We have neurons. What we compute, they're connected to other neurons. The signal is a real number passed from one neuron to the other. Number of mathematical details, they're not new. Deep learning is new. Neural networks are not new. This model was proposed in 1943. The first computer simulation of a neural network is from 1954. People were using neural networks to model machine learning tasks in the 60s. So it's not new. What has changed is the computational power and the amount of data we have has grown exponentially, which allows us to do very, very complicated things. In 1943, they were really talking about a single neuron and modeling a single neuron. In the 60s, they were talking about a sequence of just a handful of neurons. The basic idea, each one of these is a neuron. Well, the input layer is just the input that comes in. These could be individual values. These could be individual pixels, individual words, whatever you want. This takes the data that comes in, performs math on it, puts a number out. And then there's a final piece that combines that data to make the prediction. So it could be oh, this is the number of cars sold. This is my advertising spend. This is my above the line advertising spend. This is my below the line advertising spend. This is my competitive information, whatever it is. It comes into these, and this is my projected play in the next month. All it is, very simple idea. There are a couple of different things. Feed forward networks. This is not usually considered deep learning. These have been used going back into the 60s. The data purely moves from left to right. So if you go back, all of the calculations purely move this way. Recurrent neural networks allow information to flow backwards. So if you think about this picture, this value could influence this value and you get a feedback loop. It's getting closer to the way the brain works. It's still not perfect. Deep learning means deep neural networks. That's all it means. This picture I've drawn for you, it just means I have a bunch of hidden layers. They can be recurrent. They don't have to be recurrent. They can have very complicated structures in them, but it simply means I have multiple layers. They are amazingly powerful in what they do in images, in video, in audio, in language. The interesting thing is tabular data, the kind of data we deal with in business most of the time. Think of Excel. Excel holds tabular data. Your database holds tabular data. When I look at your player club members' behavior, fundamentally that's tabular data. Deep learning doesn't actually perform that well. It's outperformed by much simpler techniques in the same training time. So the real key takeaway here is when people are coming and talking about deep learning models, neural networks, and so on, and they want to solve churn, it may work, don't get me wrong, but the buzz risk is much higher, right? Simply because there are other tools that use simpler techniques that tend to be faster and cheaper that work just as well. There's another problem with deep learning. You may have heard about adversarial examples. We'll explain exactly what this means. I think the way to think about it from a metaphor is this is illusions, or Deidre, if you just type a chat message, I should be able to pick it up. These are illusions, optical illusions. If you think about it as the human, if you see a shadow move off to the side and you think, oh, that looked like a person, and then you look over there and it was just a shadow, right? You can think of this as an adversarial attack. It's something that your brain, that neural network, interpreted incorrectly. So let's give some examples. Neural networks suffer from these far more than the brain does. We have issues, but if I take this image, add some noise, and then what is the thing going to see? So I don't even know what that is. We have a insect and a dog. We add what looks to us as humans, very moderate noise. The combined picture on the right-hand side, we're still going to recognize as exactly the same thing. This is a real example. This is taken from a paper. Someone pointed this out on a model they had built. And yes, the model identified all three of these as ostriches. This is the danger of neural networks. And you see this, and people keep pointing this out. If you follow things like Tesla, Tesla has some problems where some people discovered that they could confuse Tesla by putting random signals on, or random pieces of tape on street signs and confusing the auto driving system. That's what these are. Similar example, we have a picture of a panda. It's not real great. Remember, these are classifications. They're giving you a percent. It thinks it's about a 58% chance of being a panda. We have what looks just like noise to me. Interestingly enough, the model thought it was a nematode, a very small singular cellular animal with a very low confidence. When you add them together, you get this image, which I think we'd all agree is still a panda, that it's now exceedingly confident that it's a gibbon. Again, it's one of the ways you can confuse, trick these deep learning models. It's an active area of research as to why this happens. It's just something to keep in mind when people begin talking about, oh, these things are almost human level intelligence, are they sentient, these sorts of things. Until we get a handle on this problem, I have my doubts if it's this easy to confuse. So now let's move in and talk a little bit more about deep learning now that we have some idea of what the different techniques mean. Remember, the purpose of machine learning, we're taking historical data, historical examples, the behavior of your players over the last month, 6 months, year. We're building a mathematical model that we can use to make future predictions. Now, I should say that that's one way to think about it. It's the way we mostly talk about it. So we can use this to forecast, if I do X in my marketing budget, this is what I would expect to see in play in the next year, next month, whatever it is.
Andrew,
Yeah.
is that, I just want to put it in terms that my brain understands. Is that kind of like we know when we drop a particular type of offer that we're going to be able to get this much revenue based on the past? So
yeah, it's building exactly that, only mathematically. So you're building it through experience, which is probably very valid because you've done it enough times and you see a regular uptick. What this is saying is, yes, we can build that. And the advantage of that model is now you say, oh, I want to drop 2 different offers that I've never tried together. Hopefully the model can now do a better job of teasing out the impact of one, the impact of the other, and hopefully get some sense of the interaction between the 2 of them.
Okay, so that seems extraordinarily valuable to me as a casino marketer.
Oh, yeah, absolutely.
Is this something that requires some level of computational skills, or is this kind of like you could still do this in Excel if that's what you've got to, if that's what you have available to you?
So you can probably do it in Excel. You probably need a little bit of skill to do it, a little bit of training. There are some platforms that make it much easier to do. There's a handful of companies that sell effectively data science in a box solutions, where you'll take your data, you'll work with them to get it formatted right, and they'll begin making it. As a marketer, I don't know if you ever use Nielsen. I don't know if the casino industry really makes use of Nielsen. When I was in consumer electronics, we used Nielsen all the time. Nielsen is building linear regressions, which you can do in Excel. They're not doing it in Excel, but they're building linear regressions to do exactly that, where they can say, oh, if you add this many views of a billboard, you can expect to see X come out. And right, if I can make that same prediction, I can also use it to explain where my marketing budget drove stuff when I ran it too, right? Because as a marketer, you've got 2 questions. How do I build future campaigns, but also how do I evaluate past campaigns? The same model can be used to say, well, okay, I know X happened, and I built my model to forecast that. Well, what happens if I wipe out this activity? I set it to 0. I clearly can't do it in the past, but my forecast will change. And if everything else was the same, it effectively says, oh, campaign X drove this % of my past value. It's not perfect because it's never going to be 100% exact, but it's directionally correct. It's more than directionally correct. It's actually reasonably close most of the time. So it's a really nice way to go both ways.
So this might be a good tool for, I know that there are many casinos that I've talked to across the nation that have been sitting on programs and promotions that they've always done, right? Every Monday we do this, every Tuesday we do that. And so something like this could possibly give them a bit of a forecast as to, if you do away with this, what is
Yeah,
really-
I mean, we'll talk about it next time, because one of the challenges is it only can learn what it already saw, right? And if you read the comment, it's because of what it saw it was based on. So if you've always given, right, if I have 100 ADT player and I've always given them exactly the same offer, the model actually doesn't know how they're going to behave if you change that offer, right? Because it's never seen anything different. So that's one of the challenges. There are subtle ways around it. That's where you need a data scientist to come in and say, there's ways to estimate it. They're not perfect, but they might help. But yeah, I when I talk to casinos, it always surprised me that they wanted to optimize their players club promotions, but they never really thought about optimizing their entire marketing budget, which may actually be a much bigger opportunity and actually easier to do because there's fewer levers, to be perfectly honest. It's a simpler model. And there's two stages we need to think about. There's development, and then there's the scoring, predictions, and production. So development is building that model on historical information. Scoring, prediction, production is using that. So that's exactly like you said, Julia, that's, okay, I want to know if I run this campaign next month, what is it likely to do to my bottom line? Or maybe it's, what was this campaign worth to me the last time I ran it? That's a scoring or a prediction or a production environment. And this can be ad hoc, infrequent, like we're talking about here, regularly scheduled, like I make a decision about all of my patrons, all my players club members once a month or once a week, however often you want to reach out to them. Or it can be in real time that I have one of my hosted players just came onto the floor. We noticed they were there. We have a number of models that we use to track them, and we're actually pinging the host to say, this is what's happening right now, or this is what's likely to happen. All of those are possible. So this is a famous quote. It gets thrown around in the data science community. I think it's almost become a joke among the data scientists. This is really, really important to understand from a marketing perspective. That model, when I say I built a model to forecast my marketing spend versus the revenue in the next month, that model will be wrong. And it will be wrong for not just mathematical reasons, because there's going to be errors in the process, or the algorithms are going to make assumptions that aren't true. I'm going to be missing information. So think about revenue and think about the impact of unemployment in your market, right? As unemployment goes up, that's going to affect your revenue numbers. Is unemployment in that model? Maybe a new business came in. How do you keep track of all of those things? There's going to be outside factors that you're not taking into account that are going to influence, and influence in some cases very strongly. We can all think back to the painful looking at April 2020 casino numbers, which none of us would have gotten right if you had asked us in February to forecast what April was going to look like. Or to be perfectly honest, what July was going to look like in February. We might have thought April was going to be bad, but no one thought July was still going to be bad. So you're going to miss those. The key is it useful enough for me to make better decisions than I can make today? We've got about 15 minutes left. So we've got just the life cycle, just to help you understand. This is what a data scientist thinks about. This is important for you. This is what business problem am I solving? This is key. You get this wrong, it doesn't matter what else you do. We'll spend a fair amount of time on this next time. We need to get the data. Casinos actually have really good data compared to a lot of industries, so the data acquisition tends to be relatively easy. The data scientist then goes into this loop of exploring it, getting it ready, building the model, evaluating the model, and they tend to do this over and over again before they're finally ready to turn it loose on the business. So deploy is make predictions and give it to the business. it's actually important for the business to be involved in all of these steps, because there are going to be questions where I'm looking at this and I'm saying, this data doesn't make sense. What's going on here? And it's going to be those insights of your day ends at 3 in the morning or 5 in the morning, as opposed to at midnight. Your data scientists may not understand that. And so you need to be able to give them those insights. Where should you focus? Focus on the beginning and the end. Get the use case right. Is this a business problem you need to solve? Right? Don't solve the wrong business problem. And then in production, this is where the money is. Right? This is where you're making your business decision and driving it. In a study a couple years ago, 90% of models never make it into production. If that model never makes it into production, it has zero chance of returning any value. People are seeing 1.3% ROI for data science projects. That's absurdly bad. I've been on projects that have driven hundreds of millions of dollars in ROI, so I know it's possible, but people don't worry about it. So we'll spend a lot of time talking about where this goes wrong, what you should do about it again next time. But these are the things to focus on. As I said, this doesn't require automation. Those cases, looking at marketing spend, what should I do next time? It's what I call ad hoc processing. It's happening as I need it. It could be automatic processing. It could simply be monitoring what's happening. But this is the key. When you start at that use case, you need to know what production looks like. And this is the other challenge. Too many data scientist teams forget this. They forget this is where the value is. They think they're in an R&D arm. What's the research? What's the latest technology? What's the cool, fun thing to play with? A solution 5 years from now, when I could give you something quick in 2 months, the quick in 2 months will win every single time from a business perspective. The data scientists don't seem to think about that, or too many of them forget about that. So things that you can think about, pricing. So I don't know if from a marketing perspective, how much influence you have on pricing various things in the casino, but absolutely understanding the impact of pricing on total revenue is key. We talked about that campaign piece. I refer to that as marketing mix. So it's marketing mix modeling. It can be used to explain what happens, but it can also be things like I do that monthly mailing list, I do marketing. If you have collections problems, and then we have decisions that happen on an ongoing basis. These have some challenges because now I need IT involved, right? If I'm going to automatically send a message to the host every time one of their players shows up, IT needs to be involved, right? Someone needs to do that IT plumbing. The data is oftentimes different between the data you're storing in your data warehouse that has come in over time, whereas I've got data fresh coming in from the system. Someone's probably messing with it. It may not look exactly the same. So there's things that go wrong when we do automated model decisioning, but there's a huge amount of value from that single use piece. And now I'm going to close by talking about model performance. So this is a generic topic, but it's very important to understand when a data science team comes back to you and says, this is how my model performs, what they're thinking about and why you maybe should not care, to be perfectly honest. Model performance is important. The way they think about it is not the way you should think about it. The first piece is, please ensure they evaluate their model on data that they didn't use to build that model. Remember, the goal of this is to be able to forecast the future. I don't know what the future looks like yet. I want to model that the best I can. The best way to do that is take data from 6 months ago and build my models, take data from the next 6 months and evaluate my models. I'd never seen that data before. It's brand new. I love Google. So much.
Hey, Andrew, while you're getting to your current slide, Dee Dee asked a question about data. I don't know if you
Yeah.
saw it.
I didn't. It didn't come up on my chat screen. Could you read it to me?
It's in the Q&A. She wants to know if she should ask her AI company to disclose their third-party data that identify underlying trends. If their third-party data isn't relatable, will I get the right results?
That's a really hard one. I mean, third-party data tends to be licensed in such a way it can be hard for them. What I would recommend is taking data you know the result of, right? So think about it this way. It's actually, weirdly enough, perfect for this slide because it's exactly that. They had data they built their model on. You have data that's going to look like the data you want to use going forward, but you have that data from 6 months ago. Ask them to do the evaluation there without telling them the result. Just give them the data they need to make their prediction, and then compare what their prediction is to what you know, the ground truth of what actually happens. And in fact, that's what you want your data scientists to do all the time, is to some data I build on, some data I evaluate on. I only ever want to see performance on that data I only evaluate on. And there's a number of mathematical reasons, but really the goal is when the model sees new data, will it perform well? We talk about overfitting. So imagine I have this graph, it's the same data in all three cases. I can draw a straight line through it. It's not a bad fit, but it's not capturing the oscillations. I can connect every single data point. Well, that's interesting, but do you believe that that's really what was happening in this situation? Probably not. You probably believe it's something a little bit closer to this smooth curve that fits through it. And the problem is, if I only evaluate my model on the data I see when I build it, it's going to try to build this because it's going to try to get it so there's no error. That's not what you want. And that's the risk. You're always looking for this kind of curve. Just another way of thinking about it, you don't really need to deeply understand this, but I talked about time-based of 6+ months ago to train, 6 months to now to evaluate. Oftentimes it doesn't matter if it's temporally separated like that. I could simply randomly assign. If I take everyone who played last month and I just randomly select 80% of them, build my model on that, and evaluate on the other 20%, that should work as long as there's no correlations between the 20% I evaluate on and everyone else. That's very traditional. It's called a train test split. So if you've ever heard that, that's all they're doing. The 80% I build my model on is called train. And then the 20% I evaluate on is called test or validation. So train test split, there's a number of ways to do it. You may hear about cross-validation. Cross-validation is actually exactly the same thing, only done in a more complicated way. So I take my data, ignore holdout for right now. You can think of this as a business person, I always keep a little bit of data on my side that I make them test without letting them know what the results are. That's how I know what's really happening. Break the other piece up into 5 pieces, 20% a piece. Pick one as my test set, use the other 4 to build the model. And I can do this 5 different times. The reason you might do this is that there's some randomization that's happening. It gives you just a better sense of how well that model is going to perform going forward. So if you hear cross-validation, it's just a more complicated version of train test split. Not really that important. It does mean they are doing the validation correctly. One key problem with this approach. Let's think about churn. Let's think about every time the person comes in. I called them transactions. I stole it from a banking slide. Think of it as plays. So days played. So each of these days they came in, this was the last day they came in. I define that as the day they churned. We can argue over the definition of churn. I'm more than happy to. There's a lot of good arguments, but I want to be able to say that that's their last date of play. If I use that prior solution of I just randomly select these to train on, what I may end up saying is these are going to be my training observations. This is going to be my validation or test observation. There's a problem here. I know this individual played after I'm going to test to see how well my model does. I can have data leakage. So I actually know more in the modeling time frame than I do in validation. This isn't the way the world works. Fundamentally, I would never have a situation of I know after the fact what the person did. So this is what we mean by target leakage. We're effectively using the future to predict the past. So there's some real problems with this. There's some solutions. Just be aware of this. Whenever you've got time involved, make sure that team is careful. Last thing, I just want to define what they mean by accuracy. So let's think about binary classification. Will they churn, won't they churn? There's two dimensions I can think about it. Did they actually churn? Did they not churn? Did I predict they would churn? Did I predict they would not churn? Right? If they actually churn and I predicted, I got it right. That's a true positive. If they didn't churn and I predicted they wouldn't, that's a true negative. If they didn't churn, but I predicted they would, that's a false positive. And if I predicted they would churn, but if they did churn, but I predicted they wouldn't, that's a false negative. So these are the four possibilities of a prediction in binary classification. When people talk about accuracy, it's what percentage of the predictions, the true positives, they were going to churn and I predicted they would, plus they didn't churn and I predicted they wouldn't, did I capture, right? So what percentage did I get right over the total number of people in my set? And then there's some other things, sensitivity and precision, which look at the percentage of, let's go back to that slide, the true positive, what percentage of true plus false positive did I get in my prediction? What percentage of true positive versus false negatives? So these are giving you a sense of how often I got them. You're going to see these metrics. It's my one slide with mathematical equations, and I'm going to tell you, I won't worry about any of these. I don't like these as metrics. I don't think they're useful from a data science perspective. I think they're horribly useful or horribly useless, to be fair, from a business perspective. So from a data science perspective, remember, this is a probability, not an actual value. To get these numbers, I need to predict it, pick a threshold, 0.5. My prediction is above 0.5, I say they churn. If it's below 0.5, I say they didn't churn. Why 0.5? I mean, it's halfway in between, but is that the right answer? I don't know. You should pick a threshold that maximizes important metrics. And we'll come back to this and explain how to do this. But there's a problem. I have two models, model 1 and model 2. I have 6 observations. The first 2 are true. The third is false. The next is true. The third is false. From any of these metrics, accuracy, whatever, let's pick 0.5 as our threshold. 0.9 is above 0.5. 0.6 is above 0.5. Both of them got it correct. B, both of them got it correct. C, both of them got it correct. D, neither of them got it correct. E, both of them got it correct. F, neither of them got it correct. They have the same accuracy. Does everyone see that? There's a big difference between these two models. Model 1, when it was right, was very right. Model 2, when it was wrong, was when it was right, was kind of lukewarm right? 60% chance versus 90% chance. When they were wrong, let's look at this one when they're wrong. Model 1 was, I'm wrong, but I'm not confident. 40% chance. Model 2 was very confident when it was wrong. They have this exact same performance from accuracy, but they honestly have very different underlying behaviors. And I would trust Model 1 a lot more than I would trust Model 2. Does everyone see that? Okay. So there's some mathematical metrics to get there. I really like business-oriented ones. So let's just give a real quick example from a business-oriented perspective. Let's imagine I have a churn rate of 1%. I can build you a model with 99% accuracy. Anyone have a guess how I can build a really simple model that will have 99% accurate? Yes, exactly. No one churns. I'll be right 99% of the time, right? That's not a useful business model. Okay, so let's remember the predictions are probabilistic. And I'm going to ask you a business question. What percentage of staying customers are you willing to make an offer to? Right? I can't get them all. I'm going to make mistakes. Are you willing to interact with one staying customer for every churn you prevent? Are you willing to interact with 5 staying customers for every churn you're willing to prevent? This is a business question. Think about this as the true positive rate. So what percentage of the number of people am I going to interact with do I need to actually churn for it to be worthwhile to me? At that rate, 10 staying customers for every churn I prevent, what percentage of the churn does my model capture? This is a business decision. Oops. This is the decision you need to think about. And you want your vendors to be thinking about, because this is how you're going to implement it, or this is one way to implement a churn solution. So that's what I mean by use business metrics. Think about how you're going to run the operation, how you're going to take advantage of this. So any questions?
I think Dee Dee had the one and only, but I think that you gave us a lot to think about. And I think the message I heard loud and clear is always really think about the business need and the business challenges you're having, and then find the solution that helps you get to that answer.
It's exactly right. It's the message I want to get across. The business matters, the tech. And I'm a data scientist. I love complicated solutions. If you let me build a massive image processing solution, I will. But that may take me 2 years, and that's probably not the problem you wanted solved anyways. And honestly, there's some much simpler solutions that we oftentimes should go with. And we'll talk about it, and I will give some horror stories when we meet in 2 weeks about where I saw this either go very wrong, or rather where we prevented ourselves from doing something stupid by simply asking the good business question up front.
Yeah, I mean, I think that probably, I want to say at the beginning of the 2000s, you know, all the operators were looking to build data warehouses, but they really, I feel like many of them were lost in the thrill of a data warehouse without really realizing what are we going to do with it and what are the problems we're trying to solve. And data warehouses are not cheap.
No,
right?
no. Well, this is, I'm a technologist. I'll admit it. I love toys. When you come to me and said, hey, I want you to go play with this technology toy, I'm going to be thrilled, right? And your IT department is that way. And in fact, you want them to be that way because you need them to succeed.
Yeah.
But at the same time, you need to make sure that they're actually solving the business question with what they're doing.
Very wise words. We are at the top of the hour. So Andrew, thank you so much for this. Like I said, I think we've got a lot of questions. I am going, when I send out the link to the recording, I'm going to have Andrew's contact information. If you didn't get it, Angle Analytics, both on Twitter and LinkedIn. If you've got any more questions, if you've got questions that you want to send to me, I'll forward them on to Andrew. If you've got any questions in advance of the next session, you can submit those as well. So I guess we'll see everybody in 2 weeks.
Yes, thank you all. Have a good rest of your week.
Thank you.